This video is page, I believe, 5 of your notes. It's questions 11, 12. Actually, just those two questions, I think, is all I'll probably cover on this. But it's over Dalton's law of partial pressures. Okay. And his law is basically, it's very simple. If we have a collection of gases, like in this room, you have a collection of gases, the total pressure is equal to the pressure of each individual gas that's there. Or if I have a container of gases, so if I have this container of gas, the total pressure in here is equal to the individual pressure of each gas. And the gas that causes the most pressure would be the one that there's the most of. So whichever gas has the most number of moles in here causes the most pressure. So if I had 6 moles of nitrogen and 4 moles of oxygen in here, 60% of the pressure, because there's 6 moles out of the 10 moles total, 60% of the pressure would be nitrogen, the other 40% would be oxygen. So whichever one causes more pressure is the one with more moles. So Dalton's law of partial pressure basically just says if there's a collection of gases, the total pressure is the pressure of each gas together. So the total would be pressure of gas 1 plus the pressure of gas 2. As many gases as you have. You could have 10 gases. Okay, whichever one there's the most of, again, would have the most pressure, but the total pressure would be equal to all of them individually. Again, it makes no difference what kind of gas you have. All gases exert the same pressure if they are the same number of moles at the same temperature and in the same size container. So wet gases. You're going to hear the term wet gases and dry gases. Okay, so we'll do a lab where we collect a gas over water. Okay, so the collection of a gas over water. So what you would do is you fill, like we're going to use a tube called a eudiometer, but you fill a big tube full of water, have it partially submerged in water. So that water will not come out because the air pressure out here is holding it in. You start to do a reaction of some kind that replaces the water out of here and you collect gas. So we've only collected a little bit of gas in this container. As the gas starts to be collected, it pushes the water out of here and you get more and more gas collected. Okay, so this is called a wet gas because really, say you're doing a reaction out here that produces hydrogen up here. It's not just hydrogen. You also would have water vapor. Okay, you would have some pressure from the water vapor. So it's called a wet gas because it's got not only itself, but the water vapor gas, the pressure in there as well. So water vapor pressures. Every temperature of water has a certain amount of vapor pressure. And there's a table in our book, it's page 634, that tells those. Now, a lot of kids always say, well, doesn't a huge thing of water produce more vapor pressure than a little bit of water? And my answer is no. If they're at the same temperature, they produce the same amount of pressure, because pressure is always per a certain unit, like per 1 square inch, or per a certain amount of area, okay, like PSI, pounds per square inch. So that makes no difference. So a big container, small container produces the same vapor pressure if at the same temperature. Okay, at the same temperature. So this water, we'll say if it was at 20 degrees Celsius, if this water was 20 degrees Celsius, there would be a vapor pressure, I have this one down here, that's the only reason I picked it, of 17.54 millimeters of mercury. Okay? So water at 20 degrees Celsius, pure water, always produces a vapor pressure of 17.54 millimeters of mercury. So that would be the pressure of the water in here, and then whatever other pressure there is from whatever gas we're collecting there. One just quick thing here, I've told you this before, I think, but if we have a container of water, if we heat that water to 100 degrees Celsius and we're at sea level, the vapor pressure of the water would be 1 atmosphere, or 760. It'd be producing that much pressure. 1 atmosphere, or 760 millimeters of mercury. The same as the air pressure down. Okay, so water boils when it gets to a temperature where the vapor pressure up equals the air pressure down. That's why it boils when there's less pressure, it boils at a lower temperature. It takes less temperature to get to that vapor pressure. So question down here. They've collected some hydrogen. It's 450 milliliters. So there's 450 milliliters of hydrogen in there. It was collected by water displacement at 745 millimeters of mercury and 20 degrees Celsius. So this is the total pressure. The 745 is the total pressure in the container. So our total pressure always equals the pressure of the gas we're collecting, in this case, plus the pressure of the water vapor. So the two pressures in there would be the water vapor it's producing pressure and the gas we collected. And I'll show you water displacement a couple different times. So our total pressure was 745 millimeters of mercury. We're trying to figure out what's the pressure of the hydrogen, knowing that the water at 20 degrees Celsius is this. Okay, so you'd be given a table of these, or I would usually just tell you that, hey, at 20 degrees Celsius, this is what the water vapor pressure is. So plus 17.54. So subtract that to the other side. We have our pressure of hydrogen. Move this down just a little bit. Put this on a weird angle. So 727.46. That's our pressure of hydrogen, remember. The water vapor was causing less pressure. That means there must be a lot less moles of water in this than there is moles of the gas we collected, because it's causing way less pressure. And it wants to know, what is the mass of the H2 gas? Well, we know its pressure, so in order to get its mass, we need to know temperature, which is 20 degrees Celsius. We need to know volume, okay? And there's the volume. So we can go PV equals nRT. Plug in our pressure, which would be 727, 760. Again, I guess I could ask you also how many moles of water vapor in there. You could use that pressure to do that. Or I could ask you total moles. You could use both pressures in there to do that. Our volume here is a 450 milliliter container, so 0.45 liters. Solving for N, remember this is going to be moles of hydrogen. R is 0.0821 and 293 Kelvin because we're at 20 degrees Celsius. Solve for moles there, I got 0.0179. Moles of hydrogen. A mole of hydrogen is 2 grams, so multiply that by 2. So 0.036 grams is how much is in there. Next page on there. Very similar problem. I don't know if I necessarily need to do this whole thing for you, but so they collected some gas. Oops. Put it up for you. It tells us the total pressure, so there's our P total. There's the volume. Also the partial pressure of hydrogen. So we would have to look up the water vapor pressure at 25 degrees Celsius. Okay, go to the back of the book. There's an appendix in there that's got that in there. It is 23.76. So water at 25 degrees Celsius is always 23.76 millimeters of mercury. So our total pressure, 647, equals the pressure of the hydrogen again, plus the pressure of the water. Subtract that over. The hydrogen pressure is 623. Millimeters of mercury. So that's the pressure caused by that. Sorry about the shiny light in the middle there. I want to know how many moles in grams of hydrogen. So same thing, I'd go PV equals nRT. There's the pressure I would use, because we want to know just of hydrogen. There's your volume, temperature is 25, you can solve for that. I'll tell you the answer there is 0.0228 grams of hydrogen. So I'll let you guys just try that one. Last part here, what is the volume? So we're looking for a volume, looking for liters. 2.4 grams of CO2, saturated with water vapor. Again, that's called a wet gas. If I say the gas is dry, that means the water vapor has been removed somehow. At 27 degrees Celsius, if the pressure on the gas is 747. So I'll tell you the water vapor pressure at 27 degrees Celsius is 26.74. So our total pressure is 747 equals our pressure of CO2 plus the pressure of the water. Subtract that over the other side. Our pressure of CO2 is 720. 0.26 millimeters of mercury. And again, once we know the pressure, we can pretty much do what we need to do. So we're going to go PV equals nRT. We've got a pressure to put in for just CO2 because we're only worried about CO2. So we can go pressure is 720.26 over 760. Trying to solve for the volume, trying for how many liters of gas we have. Moles, we have 2.4 grams of CO2 divided by the mole mass to get the moles. So 2.4 over CO2 is 44 grams per mole, 0.0821. Temperature is 27, so that'd be 300 degrees Kelvin. I got an answer of 1.42 liters when I solved that. That'd be just the amount of space the CO2 is taking up.